So this is going to be the last video in this little series. We've looked at all the basic stuff to do with fields, but this one's going to examine the link between the field strength and the potential. So if we take a familiar field, a radial gravitational field like this, let's see what we can say about it. Well, firstly, we know that the gravitational field strength at any point is defined as the force per unit mass, the force divided by the mass at that point. And we can rearrange this to say the force at any point is the mass times the gravitational field strength. That's a very familiar formula for you. But remember that this G can change, okay? If you're not in a uniform field, and this field certainly is not uniform, then G can be different in different places in that field. Okay, so this is our first formula. F equals mg. The gravitational force on our test object equals m, the mass of the object, times g, the gravitational field strength. Right, what else can we say? Well, we know that if we change the height of the object, we change its gravitational potential energy. Okay. Now instead of using height, I'm going to use delta r radius, but we're thinking the same thing here. So for a given point, we're going to use r, the radius, to be our measure of distance. So if we change the radius, if we move the object from there to there will be a change in gravitational potential energy. Whoops, I keep doing that. So, what is the formula for that? Well, the change in gravitational potential energy is going to be the same as delta W, the work done moving the object from the lower height to the higher height. So if W stands for work done, and the work done is the force times the distance, and the force is given by mg, and the distance is given by, delta r. Okay. Now, really, I've just told you that this g can vary. Okay, and we're using this g here as if it's a constant. So really, this is only valid for small changes. Small changes are usually shown with a small delta. So, for example, mg delta r. But in the textbook it uses the capital delta here, so I'm using the capital delta, but just be aware that this is really only going to be true for small changes in height. Okay, we can use this expression. Okay, let's keep moving. Where can we go from here? Well, we've defined potential as the energy per unit mass. So the change in potential, delta V, is going to be the change in gravitational potential energy divided by the mass. This is the formula for the change in gravitational potential energy, mg delta r. If we divide that by mass, then the m's just cancel and we get g delta r. So the change in potential is going to be g times the change in distance r from the centre of the object. Now remember, these really should be small deltas. This is only really true for small changes. Okay. Now we can already start to think about something interesting just by pausing here. I'll get rid of this stuff. Now, if we, for example, defined ground level as 0 potential, if we go up a big delta R, the potential is going to increase, let's say, to 10 joules per kilogram. If we go up another delta R, which is the same, how much is our potential going to go up by? Well, as we get higher through these big changes in height, G gets smaller. So this one would not have a potential of 20. It's going to be something less. Okay. Now, it's often nice to have potentials that go up in equal increments, so 0, 10, 20, and so on. So we're going to get rid of this potential and just think for a moment, this equipotential, just think for a moment. If we want the same change in potential, but G has got smaller, then our delta R for the next equipotential must be bigger. So the next equipotential must involve a bigger jump. So this delta R is smaller than this delta R to get an equal increment from 0 to 10 to 20 joules per kilogram. So that's the first thing to note. I'll just rub some of this stuff out so we don't get too confused. Now we can also rearrange this to make G the subject here. G is then delta V over delta R, which is sometimes called the potential gradient. So the field strength at a point is the potential gradient. How much the potential changes with distance. Okay, so you can kind of imagine that out here, as the equipotentials get further and further apart, as we're moving our test object, the potential is changing quite slowly. The potential gradient is low, the field strength is low. As we get closer to the surface, the potential is changing more quickly, the potential gradient is more, so the field strength is more. You could kind of imagine this like these contours representing height. Okay, if I just add in another contour that gets even further apart, okay, these contours would represent something with a very shallow gradient. This would be a weird sort of hole in the ground. If these numbers really corresponded to the height, this would be some sort of weird hole in the ground that got steeper and steeper and steeper and steeper as you got closer to it. So the gradient would be shallow and then steeper and then steeper and then steeper. But this isn't height, this is potential, and the potential gradient corresponds to the field strength. So the closer together these field lines are, the closer together the contours are, if you like, the steeper the gradient and the greater the field strength. So this is quite tricky, this slide. There's a lot going on here, but it's important to see this link between the field strength and the potential, and also just remember that really these should be small deltas, okay? Or if you were doing maths, this would be a derivative. So just to finish off, really, a little bit more on these equipotentials, just to reinforce what we've just said. So in a radial field, the equipotentials are spheres, and they're spheres that get further and further apart for the same increment of potential. Okay, so the equipotentials are spheres that get further and further apart. Exactly how they get further apart we'll deal with later, but that's enough to say for now. And one more thing on equipotentials. If you move an object around an equipotential, no work is done and there is no change in potential energy for the object. So if you took a ball and rolled it all the way around the surface of the Earth, anywhere you were on the surface of the Earth, as long as your height hasn't changed, you are on an equipotential. No work has been done against gravity in moving that ball around, and the gravitational potential energy of the ball has not changed. Okay, so if you stay on an equipotential, you do no work against, in this case, gravity, and the potential energy of the object doesn't change. Likewise, if we imagine a satellite orbiting the Earth in a perfectly circular orbit, as it moves around, there is no change in its gravitational potential energy. Whoops, there was there. There's no change in its gravitational potential energy. There is no work done on the object by gravity, so it keeps going around at the same speed in that case. We'll just quickly have a look at the uniform field as well, just to reinforce that. So likewise, if I drag this object around a uniform field, if I keep this object on an equipotential and move it along an equipotential, I do no work against gravity, and the potential energy of the object doesn't change. If I move it onto another equipotential, then work is done in between there and there, and the potential energy changes in between there and there. And now if I move it around this equipotential, no work is done against gravity in this case, and the potential energy of the object remains the same. So, it would be nice if that was the end, but it's not. There's just one more minor complication to add, and that is the following. The zero of potential is actually not defined as ground level, but it's defined as being at infinity. Now this initially might seem a bit inconvenient and annoying, but it's actually better that way. Previously I'd said the ground was zero potential, and then this was 10, 20, whatever. But there's a few reasons why this is not that useful. A simple reason being, what if someone digs a hole? Surely now this is zero potential, and we have to increment all these up or something like that. So it's better to have potential being zeroed at somewhere and something that doesn't change. So infinitely far away from the object doesn't change, so that's where the zero of potential is defined as. And so the definition of potential, we'll just change the working definition I had before to a more formal one. The potential at a point is defined as the work done per unit mass to move a small object from infinity to that point. Now essentially, it basically means the same thing as what we said before, because in reality we're often just dealing with changes in potential, in which case the way it's defined doesn't matter so much. But this does have some really important ramifications. The first one being that for our gravitational examples, all the potentials would actually be negative. And we'll think about why that is. Now, let me just quickly chuck in some equipotentials. Here we go. Now we're defining zero potential as being at infinity, and we're looking at how much work is done to take an object from here to any of these particular equipotentials. Okay? Now actually, I don't have to do any work to get an object, a test object from infinity to these equipotentials, because it's going to be attracted. So actually, the Earth is doing work on the object. So the work done turns out to be negative. So maybe, let's say for the sake of the argument here, it's minus 50 joules per kilogram. So that means for each kilogram of mass I've got here, 50 joules of work is done on it by gravity, getting it to that point. Now if it moves even further, even more work will have been done by gravity. So that will be minus 60, and here minus 70, let's say. Okay? So as a consequence of this definition, all of our equipotentials are actually negative here for our gravitational example. That's not to say that they're always negative, because we have another example here for a positively charged sphere. Now, if we define our zero of potential at infinity and bring our test object in, remember it's a positive test object for electric fields, now I am going to have to do work bringing this object in, because a positive and a positive charge repel. So these equipotentials, if I quickly draw a couple in, these equipotentials are going to have positive values. So this one might be plus 50 joules per coulomb. Whoops, that C should be a big C, coulomb. Now I'm going to have to do even more work to get it closer, so that's going to be plus 60, and then this one here will be even more work, plus 70. So by defining the zero of potential as infinity, it does just change things slightly. We have to think about the sign of the potential carefully. Right, that is the end of this little bit on fields. We're then going to move on to looking at the specifics of electric fields and gravitational fields, but hopefully that's a pretty good basis for you.